This is the third lecture on Hamiltonian mechanics. In the earlier one, we have used Legendre transformation to define Hamiltonian, which is a function of generalized coordinates and generalized momenta and of time. We developed the Hamiltonian from Lagrangian, and then we obtained the Hamilton's canonical equations, which these two n number of first order differential equation replaces the n number of second order Euler-Lagrange differential equation of Lagrangian mechanics. And we have also shown that for conservative system for which the transformation equation does not involve time explicitly. For such cases, the Hamiltonian is equal to total energy of the system. Today we shall discuss two more aspects of Hamiltonian. Firstly, the constants of motion. We have already discussed about constant of motion in connection with Lagrangian mechanics. Constant of motion. Say we have a system which in Hamiltonian dynamics is defined by the set of Q's, P's and T. In general, any quantity F which is related to the dynamical variable this changes as the particle moves with different Q's or P's or T's. But there are certain functions, say fk, whose value does not change even if this quantities changes and the value remains all along constant. Such quantities are called constants of motion. We shall discuss this in connection with the Hamiltonian. The Hamiltonian, as it is a function of coordinates and momenta, we can write it as del H del Qi dQi dot plus del H del Pi dot plus del H del T. Now we use the canonical equation and we replace, here it is I is equal to 1 to n, I is equal to 1 to n. We replace Hi Qi dot, so this term is del H del Qi dot, I write del H del Pi, and for del H del Pi, and for Pi dot I write minus del H del Qi plus del H del D, here as Qi dot is equal to plus del H del Pi, which is used over here, and Pi dot is equal to minus del H del Qi, which is used here. So the result is simply del H del D. Now, if the Hamiltonian does not contain time explicitly, then dH dt is 0. So if H does not contain time explicitly, then dH dt is equal to 0, that is H is a constant of motion. As we have shown in Lagrangian mechanics that this is related to homogeneity of space. sorry, homogeneity of time. Another advantage that we have another advantage of Hamiltonian mechanics over Lagrangian mechanics is the situation where there are cyclic coordinates. Let us consider a system having n degrees of freedom, of which a particular coordinate, say ck, where k is equal to say 5, q5 is a cyclic. So we have degree of freedom of the system is equal to n, and say a particular k particular qk is cyclic. If so, then we know that the corresponding momenta pk is equal to del L del qk dot is equal to constant ck. Now, if we encounter such a situation, then Hamiltonian can be written as this. Hamiltonian is this q1, q2, qk minus 1, qk plus 1, qk is missing, qn, p1, pk minus 1, pk plus 1, right up to pn and t. So to say that if one coordinate is cyclic, then the number of independent variables in the Hamiltonian reduces from 2n to 2n minus 1. So for a cyclic coordinate, as if the degree of freedom is reduced by 2 in the Hamiltonian formalism, but the Lagrangian still depends on all these quantities. This is one advantage of Hamiltonian formalism over the Lagrangian formalism when there are cyclic coordinates. And this property is used in Roth's formalism. We shall discuss Roth's formalism of classical mechanics, which is a hybridization of Lagrangian mechanics and Hamiltonian mechanics. So we shall consider few examples of Hamiltonian dynamics. Especially we shall cite two examples where the coordinate we encounter cyclic coordinates. But before going to that, we want to write the Hamilton's equation in different coordinate system. So Hamiltonian mechanics in different coordinate system. In writing this first step we shall use Lagrangian, second step we shall calculate the momenta as del L del Qi dot. In the third step we shall define the Hamiltonian as summation over I Qi dot Pi minus L, and in the fourth step we shall write canonical equations. Qi dot is equal to del H del Pi and Pi dot is equal to minus del H del Qi. To start with, we shall consider Cartesian coordinate system. So we describe a single particle system in a Cartesian coordinate system. The Lagrangian L is m by 2 x dot square y dot square plus z dot square minus v of x, y, z. We consider a system which can be described in terms of a potential. So the potential V which does not depend on velocity. So velocity independent potential, that is to say we are considering a conservative system. Then Px is equal to del L del x dot is equal to mx dots and other relations like this. So we define Hamiltonian as x dot px plus y dot py plus z dot pz minus L, which on substitution that x dot is replaced in terms of px, this becomes 1 upon 2m px square py square plus pz square plus v of x, y, z. Now coming to Hamilton's equation, x dot is equal to del h del px is equal to px by m, which is simply dx, and other relations for y and z components, and px dot is equal to minus del h del x. Since this part doesn't have any x dependence, so this is minus del v del x. Since the system is conservative, it is the x component of force and the other relations for y and z components. So this is the general treatment of the single particle system, the general treatment of Hamiltonian mechanics for a single particle system in Cartesian coordinates. Then we come to the cylindrical coordinates, rho, phi, z coordinates. So this is rho, phi, z system. We know that Lagrangian is m by 2 rho dot square plus rho square phi dot square plus z dot square minus v of rho phi z. So p rho is equal to del L del rho dot is equal to m rho dot. P phi is equal to del L del phi dot is equal to m rho square phi dot, and z is equal to del L del z dot is equal to mz dot. So the Hamiltonian is rho dot p rho plus phi dot p phi plus z dot pz minus L. Now we replace rho dot in terms of p rho etc. So we get this is 1 upon 2m p rho square plus rho square p phi square plus pz square. No, this term is p phi square by rho square. Now coming to Hamilton's canonical equation, rho dot is equal to del h del rho. Now the rho, sorry, there is v of rho phi z here. So there is no rho, there is a rho dependence. Rho dot is p rho, sorry, p rho. So this is p rho by m. This is nothing but this equation. Phi dot is equal to del H del P phi. So this is P phi by m rho square. This is this equation, and z dot is equal to del H Ez is equal to mz dot. This is this equation. Now coming to P rho dot. P rho dot is equal to minus del H del rho. Del H del rho, this term does not contain rho. Here is rho dependence. So this is P phi square m rho cube minus del V del rho. This is P rho dot. P phi dot is equal to minus del H del phi. So the phi, there is no phi dependence. Phi dependence is only in V. So this is del H del V. And finally, Ez dot is equal to minus del H. So this is the general treatment. Only you need to do, you have to use specific form of V, and you will get the Hamiltonian equation of motion in cylindrical coordinate system. And finally we shall consider the spherical polar coordinate system. So it is r theta phi system. The Lagrangian L is m by 2 r dot square, r square theta dot square, r square sine square theta phi dot square minus v of r theta phi. PR is equal to del r, del L del r dot, del L del r dot is equal to mr dot. P theta is equal to del L del theta dot. This is m r square theta dot, and P phi is equal to del L del phi dot is equal to m r square sine square theta phi dot. Earlier we considered this through the this is the angular momentum and this is the moment of inertia with respect to the axis. So we define Hamiltonian H is equal to r dot PR theta dot P theta plus phi dot P phi minus L, and this becomes PR square upon 2m plus P theta square by 2m r square plus P phi square upon 2m r square sine square theta plus v of r theta phi. Now the canonical equation, coming to the canonical equation, r dot. R dot is del H del PR. This is simply PR by M. PR by M. You check that this is the equation. Theta dot. This is del H P theta. So this is P theta by mr square. P theta upon mr square. So this is this equation. and phi dot, this is del H del P phi, this is equal to P phi m r square sine square theta, which is this equation. And finally, PR dot is equal to minus del H del R. Now the relation becomes a bit complicated. First, there is R dependence, there is R dependence, and there is R dependence. So there will be three terms. So first is minus mr theta dot square, mr theta dot square, contribution from this, minus mr sine square theta phi dot square minus del v del r. This is the radial equation. Then p theta dot is equal to minus del h del theta. This is a term which depends on theta. This term has been calculated. I have mistakenly considered Lagrangian instead of Hamiltonian. So this equation needs to be corrected. This is R dependent. So 1 by R square, when we make del R of R square, this is minus 2 R to the power Q. So this term becomes, from this term the contribution is p theta square mr cube. From this term we have p phi square by mr cube sine square theta minus del r. Now coming to theta equation, p theta equation is minus del h del theta. There are theta dependence here and in v. So if we differentiate del theta of 1 upon sine square theta, so this is minus 2 cos theta by sine cube theta. So this term is p phi square contributes p phi square mr square sine cube theta cos theta minus del v del theta. And finally the phi equation is very simple. P phi dot is equal to minus del h del phi. There is no phi dependence in this part, only phi dependence part comes from here. And if we have a azimuthally symmetric situation, then potential does not depend on phi, and we shall find that p phi is a constant of motion. Constant of motion, as we have obtained in the case of spherical pendulum. We shall consider the spherical pendulum problem like now. A spherical pendulum is a pendulum or a point mass which is fixed, suspended from a point and by a string, massless string of fixed length, and the particle can move over the surface of a sphere of radius L. So the spherical pendulum problem So the situation is that we consider this is xy plane and this is the z axis, vertical plane. And xy plane is v at z is equal to 0 is considered to be the zero level of potential. So when the particle is over here, m is at r theta phi, so this the height is z, and the Hamiltonian is, Lagrangian is half m r square theta dot square. For r we write l square, l plus l square sine square theta phi dot square minus mg l cos theta. Actually the particle is at a distance z above the horizontal plane, so it will have a potential mgz, and for z we have written l cos theta. So that p theta is equal to del L del theta dot is equal to m L square theta dot, and p phi is equal to del L del phi dot is equal to m L square sine square theta phi dot. So the Hamiltonian H is equal to theta dot p theta plus phi dot p phi minus L. So which comes out to be p theta square upon 2m L square plus p phi square 2m L square sine square theta plus mgl cos theta. Now coming to Hamilton's canonical equation. So theta dot is equal to del H del p theta is equal to p theta by ml square, which is nothing but this equation, and phi dot is equal to del H p phi, this is p phi by ml square sine square theta. This is this equation. Now we come to p theta equation. P theta dot is equal to minus del H del theta minus del H del theta. There is a theta dependence over here. So this is p phi square upon ml square sine cube theta cos theta plus mgl sine theta, and p phi dot is equal to del H del phi, which is 0. So which says that p phi is equal to constant. So for spherical pendulum we say that the phi component, the azimuthal angular momentum is a constant of motion. We shall cite another very simple example in which we have a cyclic coordinate, and the phi coordinate here is called the cyclic, as p phi is a constant. We consider the projectile motion. We consider a part. This is the horizontal x-axis and this is the vertical y-axis. A particle is being projected in this direction, and we know that the trajectory is a parabolic. Say at a particular instant the particle is over xy. So if we write the Lagrangian, L is equal to half m x dot square, y dot square, and this is the potential energy minus mgy. So Px is equal to del L del x dot is equal to mx dot, Py del L del y dot is equal to my dot. So we write Hamiltonian H is equal to x dot Px plus y dot Py minus L. So this comes out to be Px square by 2m plus Py square upon 2m plus mgy. Now x dot is equal to del h del Px is equal to Px by m, y dot is equal to del h del Py is equal to Py by m. These are these two equations, and Px dot is equal to minus del h del x is equal to 0 because there is no x dependence, which says that Ex is equal to constant, so x is cyclic, and Py dot is equal to del h del y is equal to, this is y, so is equal to minus mg. Py dot is the force along y direction, and it is minus mg because the force is downward. So this is the Hamiltonian analysis of simple projectile motion. In the next class, we shall consider the Roth formalism of Hamiltonian mechanics.